This screen demo will show how Mohrs circles can be used in representing the elasto-plastic behavior in finite element analysis. The modeling will start from the linear analysis case of the previous screen demo. New analysis type is a nonlinear analysis based on the assumption of elasto-plastic material behavior. In order to change the analysis type to elasto-plastic analysis, choose Project Setup item of File menu. The Project Setup dialog is opened. Check Material Nonlinear option by clicking the box. Elasto-plastic radio button is automatically turned on. In the last demo, all quantities were represented without units. This time, the units will be specified. Click Change Unit button. Then, Unit Setting dialog pops up. Uncheck No Units item. Radio buttons are turned on for default settings of force unit, length unit, time unit and temperature unit. The settings can be altered by clicking the radio buttons as necessary. Click OK button to complete the unit setting. Unit setting dialog is closed. Click OK button of Project Setup dialog to complete the change of analysis type. In the next step, material properties will be changed. First, choose Element Properties item from Assign menu. Property dialog pops up. The drop-down list of elasticity type is set as linear elastic in the last demo. Clicking the item shows the list of available elasticity types. The elasticity type will be changed to elasto-plastic, with more Coulomb failure criterion. Select the corresponding item from the list. The elasto-plastic type has more data items than the linear elastic type. Thus, the dialog is expanded to accommodate the additional data items. Placing the cursor over a data symbol shows the yellow tip with description about the symbol such as modulus of elasticity. In addition, the tip contains the unit of the data. Let's change the modulus of elasticity to 1200 kN per square meter. And the cohesion to 10 kN per square meter. The angle of internal friction to 25 degrees. Let's check the boundary condition set in the last demo. Horizontally moving roller along the bottom edge and vertically moving roller along the left edge. The same boundary condition of the last demo is to be applied to this demo without any change. Let's change the load condition so that elasto-plastic behavior can be observed properly in the model. So, reverse the direction of the force, and increase the uniform force intensity to 20 kN per meter. Now, the modification of the model is completed. Select Solve item from Solve menu. The Nonlinear Analysis Options dialog is opened. The number of load incremental steps is set to 10. The number of iterations within each step is set to 100. There are many other options which you may change as necessary. Click OK button after completing the setting of the analysis options. Then, the equation solving process starts. The processing takes a few seconds for this simple example. As shown in the last demo, the analysis results can be represented by a contour image. In order to obtain the image, choose Contour item from Post-Pro menu. Contour Display option dialog opens. Select Normal Stress X item from the drop-down list just as in the last demo. Click OK button. Then, the contour image of the normal stress in X direction is rendered. In the case of elasto-plastic analysis, the image of plastic zone can be overlaid on the contour image. In order to obtain the plastic zone image, open Contour Display option dialog again, and check Indicate Plastic Zone item. There are 3 different dithering options of rendering the plastic zone. In order to set this option, click More option button. Then, Plastic Zone Representation dialog pops up. You may set the dithering option in this dialog. Now, the plastic zone is indicated with darker color on the contour image. The stress level in this zone reached the plastic state. This elasto-plastic behavior can easily be identified using Mohrs Circle. Select Mohr Circle item from the Post-Pro menu. Then, Mohr Circle diagram window opens. If you click a point on the stress image, there appears a small square, namely the stress square. At the same time, the diagram window shows a Mohrs circle representing the state of stresses at the center of the square. The stress square can be dragged to any position over the contour image. The Mohrs circle diagram is updated instantly to reflect the stresses at the moved position of the square. This is the same as the Mohrs circle representation shown in the last demo with the linear analysis. One display item added for the elasto-plastic analysis is the failure envelope, which is the bounding curve enclosing the Mohrs circle. Check failure envelope in the dialog. Then, the failure envelope is shown. The tau axis intercept of the envelope is equivalent to the cohesion of the material. The slope angle of the envelope is the same as the angle of internal friction. When the point of the stress square is placed within the plastic zone, the Mohrs circle contacts with the failure envelope. The position and size of the Mohrs circle is changing, while the point of the stress square is moving. However, the contact with the failure envelope is maintained, as long as the stress square remains within the plastic zone. The Mohrs circle shrinks apart from the failure envelope when the stress square moves out of the zone. As the stress square came into the plastic zone again, the Mohrs circle came in contact with the failure envelope. The contact is maintained, while the circle changes in its position and size. Nonlinear analysis goes through a stepwise solution process with incremental force application. The presently shown images represent only the final state of stresses under full application of the forces. We may need the information about the stresses in the middle steps while the external forces are incremented stepwisely. In order to display the image of intermediate steps, the solving process should be executed with an additional option. Check Keep Results of Intermediate Steps option, and execute the solution process again. Then, the stress data are computed and saved for intermediate steps as well. The contour image and Mohrs circle can be displayed not only for the final steps but also for the intermediate steps. When the contour image is rendered, there appears the Multistep View panel to control the step for display. In this screen demo, the forces are assumed to be applied in 10 steps, with equal increment at each step. The display step can be selected using the drop-down list, or using the scroll box of the Multistep View panel. This is the stress image at step 1, and step 2, and so on. The changing stress image can be displayed while changing the display step. The Mohrs circles for the intermediate steps can also be displayed after solving the additional option for intermediate steps. Choose Mohr Circle item from Post-Pro menu again. Mohr Circle diagram window has additional items for selection of intermediate steps. Drop-down list of step number, and scroll button. The Mohrs circle is small at the first step. It grows larger and larger as the step progresses. The Mohrs circle grows larger due to increasing stresses as the incremental step progresses. And the Mohrs circle touches the failure envelope at a certain step. The contact with the failure envelope indicates that the stress square reached the plastic failure state. As the step progresses further, the Mohrs circle grows larger, while keeping the contact with the failure envelope. All the steps can be displayed in one image. Check Multi-Step Images option. Then, the Mohrs circles from step 1 to 10 are displayed together. When the stress square is moved, all the 10 Mohrs circles are redrawn. If the display step is scrolled or selected, the Mohrs circle of the corresponding step is highlighted in gray color. We can examine the elastic and plastic behavior using the Mohrs circles. The stepwise growth of the Mohrs circle shows the distinction between the elastic and plastic states. This is the end of the demo about the use of Mohrs circle in elasto-plastic analysis.